Good morning, everyone. In today's lecture, we are going to talk about the appendix of Chapter 7. If you remember in Chapter 5, when we talked about the consumer theory, the appendix of Chapter 5 was devoted to the graphical representation of the consumer problem. In other words, we wanted to reach the consumer equilibrium through a graphical representation. And in Chapter 5, we looked at the indifference curves and the budget line, and we used them to reach the consumer equilibrium, which happened at the point of tangency. Okay, and we were able to reach the equimarginal principle, okay, which is the equation that guarantees the maximization of utility for the consumer through the graphical representation. Here we are going to do the same, but for the theory of the firm. So in the appendix of Chapter 7, we are going to look at a graphical representation of the producer's problem, and I will show you how we are going to reach the least cost rule using a graph. But before moving to the graphical representation of the producer problem, I will give you a numerical example of a production function, as will be shown in the next slide. From this example and from this production function, I will be trying to confirm a number of concepts that we have studied before. The first concept is the law of diminishing returns. I will be using the next matrix or the next example to show you or to confirm the idea of the law of diminishing returns through an example. I will also be using the same example to show you what we mean by constant returns to scale. If you remember this concept we studied before, and we're going to confirm it using this example. We're also going to use this example to show the idea of having many production functions and the fact that the firm has to choose the one that will minimize its cost of production. Okay, so let's look at this numerical example. It's an example of a production function where we have this, it looks like a two-dimensional figure where we have on the x-axis the amount of labor used, and on the y-axis we have the amount of land used, okay? And in the middle we have the amount of total product or the level of output that will be produced using different combinations of labor and land. Okay, so we are going to use this numerical example, as I said, to clarify three of the concepts that we studied before. The first concept is the concept of the law of diminishing returns. If you remember this concept, or the law of diminishing returns, it showed that as we increase one input to the production process and hold the other inputs constant, the marginal product of the varying input will, at least after some point, decline. Okay, so this is what we meant by the law of diminishing returns. So let's try to illustrate this using the numerical example that we have in front of us. So let's hold land constant in this matrix or in this figure by sticking to a given row. By sticking to a given row, we are keeping land constant. Okay, so let's say that we're going to stick to row number 2 where we are having 2 acres of land used. Okay, and we are going to fix this. Now let labor increase from 1 unit to 2 units, from 2 units to 3 units, and so on and so forth. Okay, so now we are fixing land. This will be our fixed factor of production, and we are going to change the variable factor, which is labor. So let's say we are going to change it from 1 unit of labor to 2 units, and from 2 to 3, and so on. What will happen to Q, or to the total product, or to the amount of output produced in this case? Let's see. As labor goes from 1 to 2 units, the level of output increases from 200 units to 282 units. This means that it increased by 82 units. Remember that we are sticking to 2 acres of land. This will be our fixed factor. And we are just changing the amount of labor used. Okay? But the next dose of labor, adding labor from 2 to 3, will only add 64 units to total product, which is the 346 minus the 282. What does this mean? As you can see, the adding labor from 1 to 2, this second unit of labor added 82 units to the total product, but the third unit of labor only added 64 units. And this is what we mean by the law of diminishing returns. What is the intuitive justification of it? You all know the intuitive justification of the law of diminishing returns, which is the fact that the law holds because the fixed factor decreases relative to the variable factor. According to this explanation, each unit of the variable factor, which is our labor, has less and less of the fixed factor, which is land in this case, to work with. So it is natural that the marginal product of labor will decrease in this case. Okay, so this is the first concept that could easily be verified from the figure or from our numerical example, which is the law of diminishing returns. What about the second concept? The second concept that I want to stress on is the constant returns to scale. So, if constant returns to scale applies to this example, we should see the following. We should see that output should increase in the same proportion of the increase in all factors together. Remember that constant returns to scale, increasing returns to scale, and decreasing returns to scale, they are different from the law of diminishing returns. Why? Because they only apply when I'm changing the scale of production, which means that I'm changing all factors of production together. Okay? It's different from the law of diminishing returns where I'm fixing one factor and only changing the other. Okay? So in this case, if constant returns to scale apply, we should see that output should increase in the same proportion of the increase in all factors, which means that when labor increases from 1 to 2 and land also increases from 1 to 2, i.e. when the two inputs I'm using double, if I'm going to double the two inputs I'm using, we should get output to double as well. Okay, if this happens, then constant returns to scale applies. It also means that if labor increases from 1 to 3 and land increases from 1 to 3, which means that if I triple my factors of production, output should also triple. Okay, so let's check if this is satisfied in our table. In the table, in the first move, which is a move when inputs were doubled from 1 to 2, from 1 labor to 2 labor, and from 1 land to 2 land, to 2 acres of land, we go from 141 as total product to 282. This is clear from our table. Okay, so using just 1 unit of labor and 1 acre of land, the total product was 141. When I jumped to 2 units of labor and 2 acres of land, i.e. when I doubled my inputs, as you can see, output reached 282, which means that output doubled as well. So this confirms that we are having constant returns to scale. What about if I triple labor and land, moving from 1 labor to 3 labor and from 1 acre to 3 acres? You can see that output reached 423, which was initially 141, which is a tripling of output as well. So all these examples confirm the idea of constant returns to scale that we are having in this example. The third concept that I want to confirm in this example is the idea that every firm will be facing many production functions, okay, and it has to choose the one that should minimize its cost of production. So let's look at the level of output Q equals 346. As you can see from this matrix, okay, there are different combinations of labor and output that could result in this level of output of 346, which are 1 unit of labor and 6 acres of land. This was going to produce 346 as total product. We could also produce the same level of output using 2 units of labor and 3 acres of land. Okay, we could also produce the same level of output using 3 units of labor and 2 acres of land. Okay, and finally using 6 units of labor and 1 acre of land. This confirms the idea that any producer will be facing many production functions, in the sense that there are different combinations of the inputs of production, okay, that could be used to produce the same level of output. But which one will the producer choose? He will definitely be choosing the one that should minimize his cost of production. Okay, so in this example, okay, the producer is going to calculate the total cost associated with each of the 4 options or the 4 production functions that I mentioned, okay, and this will be in another slide. Okay, he's going to calculate the total cost and he will be choosing the one that will minimize his cost of production, which will be production function employing 3 units of labor and 2 acres of land. This is the one that he's going to choose, although many others can produce the same level of output. However, he is assuming that he's trying to minimize his cost of production, he will be choosing the one that will minimize his cost of production. And how can we know this? We have to calculate the total cost associated with each production function of the 4 I mentioned. Okay, and this is clarified in another slide. Okay, but for the engineering department in any firm, okay, it doesn't make any difference which production function to use, because for engineers, they only care about the total level of output. But for the CEO of the firm, the chief executive officer, who cares about minimizing the cost of production, he will definitely be choosing the one that will minimize his cost of production. Okay, so now we were able to use this important table or important example to confirm 3 concepts: the law of diminishing returns, constant returns to scale, and the idea of having different production functions, and the firm has to choose the one that minimizes its cost of production. Okay, so this table shows you how the firm uses the information it has regarding the different production functions, okay, that will yield an output level of 346, which we showed from the previous matrix. There were 4 production functions that we call A, B, C, and D, okay, and each production function has a different combination of labor and land that will produce this level of 346. Okay, so the firm is going to use this information on the different production functions together with the market price of labor and land, which is given to the firm, okay, in order to calculate the total cost associated with each production function. So here, labor is given the letter L and land is given the letter A. Okay, so the first production function, which uses 1 unit of labor and 6 acres of land, its total cost will be 1 times 2 plus 6 times 3, which is 20. Okay, and so on and so forth. So we can see that the firm will definitely choose the production function C, which minimizes the cost of production. We're going to move to the graphical representation of the firm problem. From the previous numerical example, okay, we were shown how a firm was facing 4 different production functions that all yielded the same level of output of 346. And the firm had to calculate the total cost associated with each production function in order to choose which production function to utilize, which will definitely be the one that will minimize its cost of production. Okay, but it will be much easier if we have another tool by which we can calculate the least costly production function for the firm. And this will be done through the use of diagrams, as we will see now. So what are the ingredients that we need in our graph? Actually, we need two ingredients, exactly as we did with the consumer problem, where we needed a set of indifference curves and a budget line. Okay, and the consumer equilibrium was at the point of tangency, right? So we're going to do something very similar here as well. The ingredients that we need to be able to reach the firm equilibrium point, okay, are the following. The first one is what we call the isoquant. What is an isoquant? It's the equal product curve. It is a curve, okay, that has different points. Each point represents different combinations of the two factors of production, labor and land, for example, okay, and all points on the same curve will result in an equal level of output, okay? That's why we call it an isoquant, isoquantity, or equal product curve. The other ingredient that we want is what we call the isocost. It is a line, okay, that has different points, okay, which represent different combinations of the two factors of production, but they share one property, which is the fact that the cost of each of these combinations is the same for the firm. That's why we call it an equal cost line. And this is what we're going to focus on for the coming slides. We're going to start with the first ingredient, which is the isoquant, or the equal product curve. So an equal product curve, or an isoquant, indicates all the different combinations of labor and capital, of labor and land, that yield an equal output level. So as you can see on this graph, we have labor on the x-axis and land on the y-axis. Okay, so we have the two factors of production on the two axes of the graph. Okay, and we have this solid pink curve. This is what we call the isoquant, or the equal product curve. Why? Because it has different points, okay? Each point represents different combination of labor and land required, okay? And they all share one property, which is that they yield the same level of output, or an equal level of output, which is Q equals 346. So if you remember from our numerical example, Q equals 346, we were able to produce this output using 4 different production functions, okay? A, B, C, and D. And each of these production functions uses different combination of the two factors of production. And this is what we get from an isoquant. Now we need to derive an expression for the slope of the isoquant, exactly as we did with the slope of the indifference curve in the theory of the consumer. So for our isoquant, the slope here represents the marginal technical rate of substitution between the two factors of production. If you remember in the consumer theory, okay, the indifference curve, the slope of the indifference curve represented the marginal rate of substitution between the two commodities that the consumer was consuming. Okay, how much will he be willing to give up of one commodity in order to be able to consume one more unit of the other commodity, and which will make his utility unchanged. Okay, this is something very similar in the theory of the firm. So for the isoquant, the slope is here the marginal, not marginal rate of substitution, because it is, when we're talking about firms, we are talking about technologies. Okay, so here the slope is called the marginal technical rate of substitution, because if I use one less acre of land. How many units of labor should I employ, okay, technically speaking, in order to be able to produce the same level of output, because I will be remaining on the same isoquant. That's why we call it the marginal technical rate of substitution, MTRS. Okay? Now we want to derive an expression for this slope or for this MTRS. So let's look at the arc between points A and B in the previous graph. We know that moving from A to B, total output remains constant. This is the definition of our isoquant, okay? Because A and B, each one of them produces the same level of output. This means that if we move from A to B, total output should not change. That is, the output lost from employing less of A, less of land, must be matched by the output gained from employing more of labor. Okay, and this can be written as follows. Delta L, the increase in labor employed, times the marginal product of labor should be equal to the change in the land, which is a decrease in the usage of land, okay, times the marginal product of land. And we should precede it by a negative sign, because here we are decreasing our usage of land and we are increasing our usage of labor. Okay, but at the end of the day, they should be equal to each other because output level has not changed. We're going to arrange these terms, okay, and we're going to get delta A over delta L, which is the slope of our curve, should be equal to minus MPL over MPA. And this is the marginal rate of technical substitution. Okay? Now we're going to move to the second ingredient for our theory of the firm in the graphical representation, which is the isocosts, or what we call the equal cost lines. So, as I said before, an isocost is a line that has different combinations of the two factors of production. However, these different combinations or these different points share one property, which is that they all cost the same for the producer. Okay? The next figure that we're going to show in the next slide shows a family of parallel straight lines representing a number of isocosts. When the market price of labor was $2 and the price of land was $3. Okay? So the firm is taking the market price of labor and land to be given, okay, which is 2 and 3 respectively, and it can then be able to draw a family of isocosts, okay, for the different combinations of labor and land, okay, and all those combinations that lie on the same isocost will mean that they cost the same for the firm. The firm is assumed to be able to buy whichever combination of inputs on the same isocost. Why? Because all these different combinations that lie on the same isocost will cost the same for the firm. The slope of each isocost, okay, must equal the ratio of the price of labor to the price of land, as we will be able to derive it in the next slide. So let's look at this graph. Okay, again, here we have on the x-axis the number of units of labor employed. On the y-axis, we have the number of acres of land used. Okay, and then the firm can draw different isocosts, okay, each corresponding to a specific amount of total cost incurred by our firm. Okay, so let's look at total cost number 1, okay, the first isocost from the origin, of course. This is the isocost where the total cost in this case will be equal to $3. Okay, what does this mean? This means that any point that lies on this isocost, each of these points will represent different combinations of labor and land used. Okay, however, each one of these points will have a total cost equal to $3. Let's look at its vertical intercept and its horizontal intercept. So if we look at its vertical intercept, we'll find that at the vertical intercept, the firm will be employing 1 acre of land and 0 labor. Okay, and we know that the market price of land is $3, which means that the total cost for the firm at the vertical intercept will be 1 times 3, which is $3. Okay? Or alternatively, if we look at the horizontal axis, 1.5 units of labor will be employed and 0 land. 1.5 times 2, which is the market price of labor, will give me $3. So this is just to confirm that any point that lies on an isocost, on the same isocost, will cost the same for the firm. So now let's move to how to derive an expression for the slope of our isocost line. So now we need to derive an expression for the slope of our isocost, exactly as we did with the consumer problem and how we derived the slope, an expression for the slope of the budget line. So the slope of the isocost is delta A over delta L, which is delta land over delta labor. To get delta A, we need 2 points on the y-axis. These points could be the vertical intercept and the point of origin. And the vertical intercept, we know, how do we derive the vertical intercept? It will be equal the total cost, okay, that could be incurred by the firm, divided by the price of land. How can we get delta L? We again need 2 points. So these 2 points could be the horizontal intercept and the point of origin. And the horizontal intercept is the total cost incurred by the firm divided by the price of labor. This will tell me how many units of labor I can use if I'm only using labor, for example. Okay? So the total cost here is like the income of the consumer. Okay? Because for the firm, suppose it has a certain total cost that it cannot exceed. And this is what will be used to determine the 2 intercepts of each isocost. The slope of the isocost will then become TC divided by the price of land divided by TC, the total cost, divided by the price of labor, which is, we can then multiply them together and invert the second one. So it will be total cost divided by the price of land times the price of labor divided by the total cost. The total cost will cancel out each other and we will be left with PL over PA, and preceded by negative sign, of course, because as you can see, the isocost is a negatively sloped curve. Okay? To use more labor, you have to decrease the quantity used of land. This is what we mean by negatively sloped isocost. Okay, so now that we understand each ingredient separately, we need to combine these ingredients together in order to help our firm decide on which production function to use, which production function will minimize its cost of production. Okay, so we're going to put these 2 ingredients together on one graph, and this should help us reach the producer equilibrium or the firm equilibrium point, which will be the least costly production function. So combining the isoquant of the firm and the different isocosts that our firm could be facing, we can determine the optimal or cost minimizing production function chosen by the firm. So let's look at this graph. Okay, again, we have on the x-axis the amount of labor used, and on the y-axis we have the number of acres of land used. Okay, and we have just one isoquant, okay, which is the pink solid curve, because suppose that our firm wants to produce a certain level of output, which is 346 from our previous numerical example, for example. And on this isoquant, we will have different production functions that could produce this level of output. Which one should the firm pick up? Production function A or B or C or D? This is what we want to help the firm decide on, which production function to use, okay, given that all these production functions will yield the same level of output, which is Q equals 346. Definitely the firm should choose the production function that will minimize its cost of production. And if you remember from the numerical example, because we just were facing 4 options or 4 production functions, we could calculate the total cost associated with each one of them, okay? And we could advise the firm on which production function to use. And in that example, it was production function C, okay? Now we want to have a tool that could help us reach this optimal production function without having to calculate the total cost associated with each one of them. Because, as we said, in the real world, firms face many production functions, not just 4, according to our example. Okay? So that's why we are using this graph. So the first step we did was to draw the Isoquant, which has all the different combinations of inputs, all the different production functions that yielded the same level of output, Q equals 346. The other ingredient was the different isocosts that the firm was facing, okay? So we had isocosts, the first isocost, which will cost the firm $3, the second will cost the firm $6, and so on and so forth, okay? So how can we use this graph in order to help the firm reach its equilibrium? Actually, the firm will keep moving along its isoquant because this is the amount of output that it really wants to produce. So it will keep moving along the pink isoquant as long as it is able to cross over to lower isocosts. Okay? So let's start from the northwest. The firm will start from point A. This is on the isoquant it wants to produce at, okay? However, A lies on a very high isocost. So the firm will keep going downward, moving southeast, okay? Crossing across another production function, which is production function B. And as you can see, this production function lies on a lower isocost, which means that it is definitely better for the firm to be producing at B rather than at A, because the same level of output will be produced, but at a lower cost. But this is still not the optimal. It will keep moving southeast, okay, until it reaches production function C. This is, as you can see, is even better than production function B because it lies on a lower isocost. Moving even further to the right, to point B, we'll find that the same level of output will be produced at D. However, the firm moved upward to a higher isocost, which means that it's not better than C. This means that the equilibrium for our firm will be achieved at point C. This is where the isoquant is tangent to the lowest isocost. Okay, so here at point C, the isoquant is tangent or just touches the isocost. Okay, at this point of tangency, the slopes of the isoquant and the isocost must be equal. And as we derived in the previous slides, the slope of the isoquant was equal minus MPL over MPA. And the slope of the isoquant of the isocost was minus PL over PA. So this means that at point C, which is the point of the firm equilibrium, okay, minus MPL over MPA will be equal minus PL over PA. Since we have negative sign on both sides, okay, they can cancel out each other, we are left with MPL over MPA equal PL over PA. By a bit of rearranging this equation, we will be left with MPL over PL equal MPA over PA. Does this ring any bells? Yes, it definitely should. Okay, so MPL over PL equal MPA over PA This is our least cost rule that we talked about previously, but the benefit of today's lecture was that we were able to derive it through this graphical representation.